Now we're discussing double integrals in polar coordinates. So, the first thing is that in polar we have um, what might be called a polar rectangular region, which looks a little bit different than your usual rectangular regions in Cartesian coordinates, since the way that um, the coordinate system works is slightly different. So, this odd sector-like shape is what is called a polar rectangle. You have some variation in the radial direction and some variation in the angular direction. Um, and so that is what is called a polar rectangle. And symbolically, it can be expressed in this format. Now, a double integral um, in the polar coordinate system is most easily handled when the region that you're integrating in polar when that region is polar rectangular, right? Just as with Cartesian, it was very easy when in Cartesian we were integrating over a rectangular um, domain in Cartesian coordinate system. The same holds true if we, instead of uh, talking about rectangular regions in Cartesian, if we talk about rectangular regions in polar, those are the easiest to integrate over. And if we do so, if we have such an expression, then we end up with this kind of an integral. So you'll notice that the inner integral is with respect to the radial direction, and it's from r equals a to b. A and b are just some numbers for radii. And then for theta, for the outer integral, it's from alpha to beta. Alpha and beta should both be angles. Um, and you'll notice that there's this additional factor r here. Now, this is because um, if you look at how the differential element for area is set up, and the book goes through some work to actually show this. I decided to skip over it because the derivation is not too important. But the idea is, as you can notice in this picture, the size of the polar rectangles changes in a way that depends on r. In fact, as r increases, as you get further and further away radially, the polar rectangle that you would trace out, the sort of differential element of area, would be larger. And it turns out that the proportion to which it increases is it's proportional to the radius. So that's what this factor r here represents. It's actually representing the fact that in the polar coordinate system, our areas are sort of warped depending on how far away we are from the radius. I should mention just as a just to relate this to future information that you'll see, this uh, this quantity is actually something called the Jacobian. And there's a similar uh, extra factor that you tack on if you're integrating in spherical instead of in um, spherical or instead of in Cartesian. So Cartesian, you don't have this additional Jacobian showing up because there's not really any area distortion. But in polar, as we are seeing in two-dimensional integrals, but also in three-dimensional integrals with cylindrical coordinates and spherical coordinates, there is going to be a Jacobian that shows up due to the warping of the way that we parameterize our space. And that topic will be roughly explained in I believe section 5.7. Okay, but let's kind of get back to just the polar. So with polar specifically, so the function should be written in terms of r and theta, right? The equation that you're or the function that you're integrating over should be converted over to polar. And whenever you have an integral in polar, there should be an r that is coming from the fact that you're integrating in polar. So you should have r dr d theta. You can sometimes reverse the theta and r So you'd have like r d theta dr, but uh, I think it's more conventional to write it in this order. Okay. Um, let's see. This is another thing that can happen, which is when your region is not precisely a polar rectangular region. So this didn't. I don't believe that this showed up in one of your homework problems, but this is a very typical kind of problem to arise, and so I think it's worthwhile to mention it. So what you might have is that the region is defined by a further radial function and a closer radial function. So which in this diagram is the h2 of theta and the h1 of theta. And you'll see that there are bounds on theta itself, a alpha and beta. So this kind of uh, general polar region, as the book is calling it, is described in this way. So the only difference between this and the um, polar rectangle is that the bounds on r were constant for the polar rectangle, whereas with this, the bounds on r are functions of theta. Okay. And then when you set up the integral, well, it's kind of as you would expect. So um, you let r range from the lower uh, value to the higher value. It's like you're sweeping along the radial direction. So along like this line in red, you'd be sweeping from the lower value to the upper value, and that's really a summation that you're doing. You're summing over the value of the function um, in the Riemann sum definition of the integral. Okay. Let's look at some examples. I tried to do my best to select some examples that illustrate what you're supposed to do with the material. I think that the problems that you're given in this section were a little bit too uh they weren't representative enough. So these examples that I'm going through, they may not completely reflect what you'll do in the homework, but they hopefully will explain how you handle these types of problems that involve integrating it in polar. So suppose you have this function. Um, you're integrating the function 3x over some region R, where R is this, and you can tell that this is a polar rectangular region. So we could do a sketch of it. It's not too bad to do that. Um, theta goes from 0 to pi, and it starts at radius 1, and it ends at radius 2. And so our region is this, perhaps you could call it a horseshoe shape. So this is the region that R is specifying, and we're performing this integral over R. Well, in order to integrate over polar, we want our function to be expressed in polar, right, in terms of R and theta. So we should recall how we convert Cartesian to polar. So in particular, you should hopefully remember that x is equal to r cosine theta, and y is equal to r sine theta. So we'll just need the x conversion formula there. That allows us to convert the expression inside, and that's why we have this r times cosine theta. And this extra r is coming from the Jacobian. It's coming from the fact that integrating in polar, we always have this r d theta. Okay. And you can see that the bounds are copied straight from the definition of the region. So r goes from 1 to 2, theta goes from 0 to pi. Okay. The next thing I do is I end up separating this integral into a product of two one-dimensional integrals, because you can notice that this function inside the double integral, it's a product of functions. You can completely separate out the r and the theta from each other. You can write it as a product of two separate functions. And so I'm using that convenient property in order to split apart this double integral into a product of two smaller integrals. That way I don't need to treat this as an iterated integral. I can um, work it out a little bit more easily, I think. If you want to treat it as an iterated integral, you can do so. It's just that it probably will use one, maybe two more steps. But so I split this, right? So the only factors that involve theta is just this cosine of theta, which gives me this integral. I have to be sure to copy the bounds correctly for the integral. So the theta integral is the outer integral, and so we copy the bounds on the outer integral. The factors that involve r are going to be the three. I decided to use the three because, well, I decided to copy the 3 over. Actually, I think there's going to be a cancellation that I didn't. Yes, that's supposed to cancel. All right. Well, anyway, so 3r squared gets collected together as being the part of the function that involves r. The 3 grouping the 3 over with this is convenient because when you integrate, you're going to have an r cubed over 3. The dividing by 3 is going to cancel with the multiple of 3, which I didn't write here because I wasn't paying attention. So this is what you would get after you do the integration, and then you should evaluate. But this evaluation is actually quite straightforward because cosine is going to be 0 at both evaluate at 0 and at pi. So that makes this entire product into 0. That's why we get that at the end. Okay. This next one, I think this time the domain R is a little bit more complicated in expression. It doesn't look immediately like well, the way it's written is not in polar. So what you need to do for this problem is you need to convert it over to polar. So notice that this x squared plus y squared, this is the quantity r squared. So this is saying that r squared is between 1 and 4, or in other words, it's saying that r is between 1 and 2. This x is also telling us something. It's going to specify what quadrant the region is supposed to be within. So x being less than 0 means that we were in these two quadrants. And so really, when we convert over this region, it's going to become the region. Let me see if did I write it at all? I did write it. Okay. So I did end up writing it, which means I'm not going to bother writing it by hand, but you see that we have r being between 1 and 2, and the angle theta is between pi over 2 and 3 pi over 2. That lands us in the second and third quadrants. Okay, and here's a sketch of the region. Probably should shade the region itself that we're integrating over. So it's this well, yeah, it is called an annular region. Sure, it's an annulus. It's a disk minus a disk. Okay. Now we were supposed to integrate over the function x plus y over this polar region. It is polar rectangular actually. So it's just that it wasn't presented as a polar rectangular region, the way that it was given. But you can tell that this is polar rectangular because, well, the bounds for theta and the bounds for r are both constants. So when you end up constructing the integral that integrates over this region, you end up using bounds that are all constants. So that's why it's polar rectangular. Okay, so again, what I do is I put r d theta, and I match up the variables for the integration. So r goes from 1 to 2, theta goes from pi over 2 to 3 pi over 2. And then to convert x and y, you use the fact that x is r r cosine theta, y is r sine theta. So that's how we get this in here. And again, you can split things off nicely to view this inner function that you're integrating over, to view this function as a product of two functions, one involving just r, one involving just theta. So again, because we can do that, we can avoid thinking of this as an iterated integral. We can instead split this into a product of two integrals, which is what I do next. I believe I have an example where I don't split it somewhere below. But yeah, so here we can split it. So I'm factoring out an r, collecting the r's together to get me r squared. I can integrate that. And then for the function of theta, it's cosine theta plus sine theta after you've factored things out. I think that's pretty clear. So you can proceed to integrate. And you don't get anything that's too bad. So I think this evaluation is pretty clear. The sine and cosine requires you to think through your unit circle. That's something that you should be comfortable with doing, but I don't know. I always have to refresh students on it, so let's see. So sine and cosine. So you have to remember that cosine is here and sine is there. Cosine is the x-coordinate, sine is the y-coordinate. Pi and 3 pi, pi over 2 and 3 pi over 2 are these points on the unit circle. So what you can tell is that cosine is going to be 0 for both of them. Sine is going to be plus 1 for pi over 2 and minus 1 for 3 pi over 2. But so the evaluation is going to be sine of 3 pi over 2 minus sine of pi over 2, right? Sine of 3 pi over 2 minus sine of pi over 2. That's a minus. And so you end up with minus 1 minus 1. That's how we get the negative 2 there. And then, of course, multiply together to get the final answer. Let's see. This one. Yeah. Okay. This one is, I believe, the one where it has to be done as an iterated integral. So the thing that makes it necessary to do this as an iterated integral is that we don't have a polar rectangular region. We actually have a dependency between r and theta in our defining when we set up the integrals. So, well, our function is that r squared sine theta times r. We have bounds for theta here, bounds for r there, and you see that this function is what's coupling r to theta. R depends on theta, so you have to set up your integral for r inside your integral for theta. In this case, the ordering is forced. So when you set up the integral to integrate over the region specified, this is what you end up getting. And I've simply collected the r over. And so, although in this case it looks, the function itself can be split into a function of r and theta, the issue is that the domains cannot be. Because there's dependency, because the domain for r, or the bounds for r, depends on theta, we can't just split these two integrals apart. We have to treat this as an iterated integral. And so the first thing we do is we integrate with respect to r. So this part that depends on theta is treated as constant with respect to integration by r. And so the integral of r cubed is r to the 4 over 4. I pull the 1/4 out right away. And we have to evaluate this r to the 4th at 0 and at 1 plus cosine theta. Right. Well, evaluating at 0 is easy. Evaluating at 1 plus cosine theta, it just inserts it in. And if we're noticing things, if we're thinking ahead, then we shouldn't do anything to expand this. What we can notice is that the subsequent integral involving theta can be done if we think of this as a u sub. Right? If we let u, I guess I should write this. If we let u equals 1 plus cosine of theta, right? And I would hope that everyone could have seen this without me saying it, but by allowing u to be this quantity inside, du is going to absorb this sine of theta. We'll have to introduce a negative just to make things work, just to make the u sub work out correctly. And then, well, then you end up with the integral of u to the 4 du, which is just going to be u to the 5 over 5. That's how we end up with this, and that's how we end up with the negative there. I believe that's a typo. Yep, that's a typo. So you evaluate that from 0 to pi. Plugging in at pi gives you -1. And so that gives you 0. Plugging in at 0 should give you 2. So you get 2 to the 5th over 4 times 5 with a negative. And so that cancels 2 copies of 2 on upstairs, giving you 2 to the 3rd, which is 8. Oh, and then the negative, right? So because this is the evaluation at 0, there's an extra negative. And so the 2 negatives will cancel. And so that's how you end up with 8 over 5. Okay. Right, and this is what I've been mentioning, that this has to be done as an iterate integral. It can't be split because of the bounds. Okay. Right. Is this the last example that I have? No, second last. Okay, so when introducing this topic, or when first encountering this topic, pretty much this is a classical example of what you can do now that you know how to integrate in polar. You're able to determine this, and it's through a clever trick. So this is a very classical integral called the Gaussian integral, and it has a kind of interesting value. Now, the trick for this is to convert to polar, but you have to be a bit clever about it. And it turns out the right thing to do is actually you want to square the problem. You want to multiply the problem by itself. The other part of the problem, instead of the variable x, you use the variable y to make you think about things more in terms of the xy plane as a two-dimensional integral, and to then convert over to polar. Now, this step here is technically a bit of a hand wave. There is some technical assumptions allowing us to be able to commute integrals like this, to be able to write a product of integrals as being a double integral. It's somewhat equivalent to the fact that of like being able to rewrite a nested sum as a being able to switch between a product of two sums, two infinite sums, versus nested sums. But that's technicality that we gloss over. So once you have that, then, well, this exponential times this exponential, right? What you do is you add the exponents, so you get this expression. And then you can notice that this is negative r squared if you convert over to polar. And so we can go ahead and try to convert the whole problem over into polar, right? When we do so, converting over to polar, we have to introduce the r as part of integrating in the polar coordinate system. And you'll notice that the bounds change in appearance quite a lot, right? So in Cartesian, we were integrating over the entire xy plane, from minus infinity to infinity, both in x and y. This is expressed quite differently when we talk about polar, because we don't want to wrap around the circle multiple times. So we only want to wrap around it once, but then let the radius go to infinity, which is what we do with these bounds. So you can see the radius goes from 0 to infinity, and the angle theta goes from 0 to 2 pi. That covers every point on the polar plane, which is the same as the Cartesian plane. And you'll notice that this is an integral that you can actually compute, whereas originally this guy it's kind of well known. This is a very typical example of a function that you don't have the antiderivative for, but this guy you do, right? So this is just a quick u sub, right? If you let u be the minus r squared, then I guess I should write it. Since I'm saying it, I can write it. Then du ends up being minus 2r dr. And so all we need to do in order to complete the u sub is we have to multiply by negative 1 over 2. That's going to introduce a negative 2 into the integral. That's why we end up with this negative 1 over 2 outside of the problem. And then we're able to just integrate it. We end up with just the exponential that you evaluate as a result of the integration. So that's why we have this term. And I'm doing something very quickly here, which is this function inside doesn't have any dependency on theta. So really we could have split this into a product of two integrals, one integral just being the integral of the function 1 from 0 to 2 pi. That gives you this 2 pi out here. This 2 pi is coming simply from the integral with respect to theta, whereas everything else is from the integral with respect to r. Okay. Now, then evaluating, right, and you should be thinking of this as limits, right? These are technically improper integrals, or this integral with respect to r was an improper integral, so you're taking the limit as r goes to infinity, and perhaps as r goes to 0, because this is kind of singular there. But so at infinity, well, this is really an exponential in the denominator, right? So this negative means it's actually the exponentials in the denominator. When you let r go to infinity, then you end up with the value 0. That's why we have this 0 here. Also, I should say that I've simplified the constants at front. And then when you evaluate at 0, and you're plugging 0 into here, that's making the denominator equal to 1. So you end up with 1 subtraction because that's the second half of the evaluation. And so we end up with pi as the computation that we've just done. And what did we actually just compute? We computed I squared. So we found that by squaring the problem, we were able to calculate this double integral, and we got the value pi. So that means that the original problem, the original integral, is actually the value square root of pi. And that is indeed the answer. It's quite interesting that this approach works. You can also check this numerically if you're not convinced by this argument. But yeah, this is a very classical example of what we're able to do once we learn how to integrate in polar. We can finally tackle this kind of definite integral, which I should maybe make a comment that this is actually a useful, this function itself is actually quite useful. This is what defines the normal distribution, the normal curve, the bell curve. This kind of function, if you think about the integral as a function that takes in a parameter for the upper bound, that ends up being something called the normal CDF. It's a useful function in probability theory and statistics. So this kind of problem is not contrived. It actually has a lot of real-world applications. Okay. Right. Now this last problem. So this might be the closest to the homework problems that you have, where you're given a problem and you're told to convert it to polar in order to be able to actually compute it. So you'll be given something that looks, it looks something like this. I mean, we've done examples like this just now, but let's see. So it's pretty straightforward to convert the function itself, right? You know that this is going to become r squared. And you know that when you convert the integral from Cartesian to polar, you have to have an r dr d theta, right? The only thing to really figure out is what is going on with the domain that you're integrating over. So the problem tells you the domain by telling you these bounds for the integral. So what I would do is to try sketching out what this domain looks like. So it's saying that x ranges from -1 to 1, okay? And it says that, well, y ranges from this negative quantity to 0. So at most, the y coordinate is 0. So that's kind of interesting. And then we have this expression, which hopefully you can tell that is the expression for the bottom half of a circle, right? If it didn't have this minus, you'd be talking about the upper half of the circle. But here we have the bottom half. And my circle is not very circular. It's a bit lopsided, but hopefully you can tell what is being drawn here. So this is the bottom half. So this integral is integrating over this region that I've drawn off to the side. That is the bottom half of a circle of radius 1. So to convert this over to polar, we can then just kind of read off what needs to happen. And that's basically the next step that I have here. So we can tell that r needs to go from 0 to 1, and that theta ranges from pi to 2 pi. From that, we can we can put all that information into the integral in polar, right? R going from 0 to 1, theta going from pi to 2 pi, the function that you're integrating being cosine of r squared, and then this extra r that is needed due to the fact that integrating in polar has this kind of area distortion. Okay, so you can go ahead and integrate from there. I believe this is, again, a simple u sub kind of problem. When I'm saying simple, I kind of mean that it's like a mental u sub. It should be a u sub that you can do in your head. You don't need to write it out completely. It's one of those guess and fudge type of things. So in particular, you would let u be this r squared, and then you'd notice that you need to introduce a 2 to be able to completely, okay, I'll write it just because it's easier to point out what it is that I'm trying to say. No, dr. So in order to replace dr with du, it's necessary to introduce a factor of 2 inside of the integral. So that's why you multiply and divide by 2, right, which introduces this 1/2. You can then proceed to do the integration, and then if you do the back substitution, you end up with this expression, 1/2 sine of r squared. So this is the integral of this. And then you'd evaluate this from r equals 0 to 1. I should also mention that this pi came from splitting this, right? You can see this is a polar rectangular region. So we were, and the function itself is a product of a function just involving r, a function just involving theta. The function just involving theta being simply the constant function 1, right? So you can then split it off, and you just have you're just integrating 1 from pi to 2 pi. That just gives you the length of the integral, which is pi. And then this evaluation is straightforward, right? Plugging in 1 gives you sine of 1, which is the only term that sticks around. Sine of 0 is 0. Okay, so hopefully that clarifies this topic. All right, that's all I've got.